Hello and welcome to today's edition of HoloTube. We are very happy that Mihailo Čubrović was able to make it today, and he will tell us about his work on factorization, chaos, and the IKKT matrix model. Take it away, the floor is yours.
Thank you. Yeah, so thanks a lot for giving me the opportunity to talk. It's really a great idea, this HoloTube. So yeah, sometimes I participate, sometimes I cannot make it, but there are always videos. So yeah, great thing. So I will tell today about the celebrated factorization puzzle and its relation to chaos, scrambling, and related buzzwords. So yeah, for about 10 years by now, it somehow hangs together, like black holes, scrambling, maximal chaos, then replicas, factorization, wormholes, and half wormholes. So lots of buzzwords in lots of papers for the last few years, and also a bit before that. Broadly speaking, the motivation here is to connect them somehow and to systematize this whole thing, to see if there's a causal relation between some of these things, and in particular to pose the problem of factorization in a setup more general than holography. So it mainly pops out in holography in relation to non-factorizing gravity, as opposed to the CFT, where we expect that partition functions of independent systems should factorize. But I want to argue that the problem is actually relevant also when there's no dual CFT, or when the dual CFT is when it's not obvious what it is. So specifically, I will work with the IKKT matrix model. This is a discretization of type IIB string theory in a certain limit. So this will be the first part of the talk, to see that we can actually discern factorizing and non-factorizing solutions, and we can try to see what they mean. So this will be the first part of the talk. This is a rather sound thing published already. Then the second part is fresh results. So chaos and out of time order correlators in type IIB matrix model, and an attempt to connect it to factorization. So yeah, here there will be several loose ends because it's still work in progress, and I'm happy about any critical comments in relation to this. And if time permits, maybe also similar thing also in the context in the context of more proper quantum chaos, so random matrices for chaotic quantum mechanical systems. But I'm not sure if there will be time for this, so this is like an appendix. Okay, so to remind you, although I guess everyone's very well aware of this, so yeah, the replica wormholes and the reproduction of the page curve has led us to the factorization problem. So a series of papers culminating in these two companion papers about 3 years ago already. So they have famously reproduced the page curve of an evaporating black hole. So first going up in accordance with the Hawking result, and then going down first going up in accordance with the result for the Hawking radiation, and then going down in accordance with the Bekenstein-Hawking entropy for a decreasing black hole. So yeah, these papers have famously reproduced this result, but at the cost of summing over several saddles, including wormholes, so including replicas or multiple boundary space-times which are connected in between. So they have a double trumpet or multiple trumpet topology, and that introduces the factorization puzzle. So according to ADS CFT, the partition function in gravity equals the CFT partition function. But then the wormholes ruin the factorization. So for one system, it's all right. So let's say we have an ADS or ADS black hole with the boundary in red, but then for two copies, two replicas, in addition to the trivially doubled system, we can also have a replica wormhole where the two boundaries are connected. So This second contribution ruins the factorization. Now in gravity, who knows, maybe we could live with the non-factorizing partition function, but we do expect the two non-interacting CFTs that and non-interacting CFTs should have the partition function, which is just the end power of a single system partition function. And then one of the first solutions proposed is, well, that ADS CFT is secretly doing some kind of averaging. So what we see is really, some kind of average partition function. And then, of course, we can easily have this. We know that averaging and the square do not have to commute. So in that case, there's no problem of principle. Now, where does it come from? So averaging over what? And is it fundamental, like some quench disorder, or emergent in the sense that we have some coarse graining like we normally have for a, well, say for a time series of a chaotic system? Now, there are many ideas. There are several very interesting papers. So I have included here a personal choice. So in some cases, it's proposed to be a quench disorder. In some cases, it's more like coarse graining. In some papers, it's argued that there's actually no averaging at all. That when you look at the correct region of the parameter space, you can avoid it completely. And some of these ideas are, well, mutually rather exclusive. Some are perhaps complementary, so referring to various parameter regimes. And the idea here is to say, okay, let's see what it looks like in in deep quantum gravity, in non-perturbative string theory. And then the natural framework for this is the IKKT matrix model. So forget ADS CFT for now, forget factorization of dual CFTs for now. Let's see if we expect in general that these partition functions factorize or not. So I'm not sure how popular it is. I decided to include a short, like 5-minute introduction to the IKKT model. If this is familiar to everybody, then please tell me and I can skip it completely. If not, so I will just remind you. So it's an idea from 1997-98. To discretize, I will come to this, discretize the shield action of type IIB string theory. So it has rich dynamics. It can reproduce, for example, brane configurations, and there are ideas to model something like black holes in this. Actually, it's supposed to contain full non-perturbative string theory. I mean, we don't have to do the usual perturbation theory in the matrix model, and that's the appealing thing about it. And it turns out, in type IIB string theory, it turns out to be zero-dimensional. So there are no derivatives, which makes it for a simpler, well, path integral structure than models like BFSS, where you actually have one dimension, the time and time derivatives. And the factorization discussion then goes along, along the lines which are somewhat similar to the zero-dimensional or time-frozen SYK model from March last year. So normally SYK is one-dimensional, right? It lives in time, but then if you freeze it, at one time point, then it becomes zero-dimensional, like our case. Although, of course, in detail, the systems are very different. So IKKT model proposed by Shibashi, Kawai, Kitazawa, and Tsuchiya. So it starts from the shield action for type IIB string theory. Of course, type IIB string theory is in 10 dimensions, but then when you discretize it, it turns out that at leading order, all derivatives drop out. And from the Polyakov, well, essentially what survives from the Polyakov action is just these commutators. So it's commutator squared of the bosonic degrees of freedom plus this term coming from the fermionic degrees of freedom on the world sheet, and then beta is just a constant which can be disregarded in this case. And basically it has to do with gauge fixing on the world sheet, but since it's a constant, we don't have to worry about it. So 10 bosons and 16 spinors, and they're all n by n Hermitian matrices. If you're interested in details, you can look at original papers or in one of the several reviews available. So let's look at the action and equations of motion. So, okay, action we have seen It's just commutators and products of matrices. Now we can look at Euclidean signature, which has well-defined partition function, always with positive definite real part. However, it may have an imaginary part in the presence of fermions, because basically these fermions, these Majorana-Weil spinors, are a bit fishy when you go to Euclidean time. So in this case, well, if you can live with the imaginary part, it's all right. I mean, it's a proper partition function as in statistical mechanics. Then with Lorentzian signature, it's always real, but well, as you would expect, it's not necessarily positive definite because you have minus in front of the time component. In particular, when doing the numerics, it leads to the same problem in quantum Monte Carlo. So this partition function in Lorentzian signature, it's more like an amplitude, right? Because yeah, it's not properly a partition function. It's more like averaging over the scattering amplitudes. Now, what do D-brane solutions look like? So remember, in 2B, you have dp brane excitations with p odds starting from d instantons, p equal -1. So they're points in not only in space but also in time. And any configuration in the matrix model can be thought of as a collection of n instantons. So it's really like n by n matrices describing branes which are made of the instantons as the elementary degrees of freedom. So a single dp brane solution, it has altogether p+1 non-zero matrix, and they come in pairs like canonical coordinates and momenta with the canonical commutator between them. Now, in particular, in the large n limit, so when this goes to infinity, then this right-hand side, the commutator goes to 0, and then it's just any random Hermitian matrices which commute with each other. And well, for the reasons of regularization, we have to bound the eigenvalue somehow. We have to introduce a cutoff. But apart from this technicality, just any pairs of random matrices, and this is where disorder naturally pops out. So these D branes, as you could expect, I mean, microscopically they're hugely degenerate, and you can regard this microscopic states as kind of effective disorder. So it's described by random matrices. Now, yeah, if you go to finite time, then there is some correction, some fluctuation on top of this, but then we can regard this as fast fluctuations or as fast degrees of freedom on top of these on top of these random matrices which are nearly frozen. So for our purposes, it's good enough to look at these strings. So just p equal 1. So for a single D string, we just have 2 non-zero matrices. For a pair of these strings at some distance and with some angle between them, we need 4 altogether. Now, for theta equals 0, right, when it's 2 parallel strings, then it's BPS and it's not interacting. Otherwise, we have an interacting system. So this is enough as a proof of concept. So like a single string or parallel strings is a non-interacting system, and also then the interacting case. Although it will turn out that at least, well, at my present level of understanding of this whole thing, I mean, interactions are not even crucial here. It doesn't differ much. Now, what are we going to average over? So we can divide the fields, as I said, into slow, quenched, or semi-classical degrees of freedom and fast degrees of freedom. And let's look at bosons for now. It's simpler. So for now, we can disregard the fermions. So yeah, A mu goes to, yeah, sorry, the way it's written here with sign of equality doesn't really make sense. Only now notice this. It should be like an arrow. So promote these frozen random matrices A mu to A mu plus, yeah, plus a fluctuation. And look at Euclidean partition function, because for now that we don't have dynamics and chaos, this is the more logical choice. So strictly speaking, the action is a path integral over both the fluctuation and the, yeah, and both the fast and the slow part. Now we can either eliminate the fluctuations or we can eliminate the frozen part or near frozen part. So in the first case, if you eliminate the fluctuations, we get what's normally, well, the background fields approach in field theory. So you integrate over the fluctuations and you get some effective action for the background fields. So this is this is logical in some applications, but in this case it's more natural to go the other way around. So eliminate A capital as a dynamical degree of freedom, and then look at these fast fluctuations. Now you can do it either by quenching or by annealing, right? So you can either fix some A mu naught configuration of the slow degrees of freedom, and then you look at the action for the fluctuations for this fixed A mu naught, or you can average the whole thing over A mu or A mu capital. So you average over the disorder, and then you get the annealed partition function, the annealed effective action for the fluctuations. So let's first look at the annealed case. It turns out that you can detect non-factorization either way, so it doesn't matter much for now. It's more of a technicality, but it's easier. Yeah, it's easier to identify wormholes and half wormholes in this case. So anneal D-branes, upon dividing the fields into slow and fast parts, you integrate over the slope pseudo-random matrices. As I said, they're random, except for, you need to introduce some cutoff. You can do with hard cutoff, which is usual in the literature, or with a Gaussian or soft cutoff. The results are equivalent. I mean, as you would expect, nothing should depend crucially on the cutoff. And so the partition function is first summed over the slow. First you sum over the slow variables, and then you study this effective action over the fast fluctuating variables. So the big issue: does the replica partition function factorize? We see that there's a natural way to introduce disorder. Actually, you don't even introduce it by hand; it's just there. I mean, just this typical D-brane fluctuation. That's what they look like. So in this case, disorder. So in this case, disorder is pseudo-random, but there's really nothing. There's really nothing random as in the sense of being introduced by hand. It's still solutions of the deterministic equations of motion. Well, strange equations of motion because they're zero-dimensional. But
excuse me, is it possible to ask a question?
Oh, of course. Sure. Don't wait till the end, please.
Yeah. Okay. Thank you. Sorry for interrupting. I just wanted to understand, given the motivation, do you really regard IKKT as not as holography? I mean, this is probably a semantics question, but I just want to understand. I mean, in what sense? I mean, BFSS you could think of as holography, right? So why not IKKT?
Well, you're right. Maybe it's more semantics. I mean, of course, we expect that. Well, I mean, since it's type IIB string theory, we do expect that it contains holography. Indeed, the most celebrated example, ADS5 cross S5, that comes from type IIB. So you're right.
But I mean, in particular, like the way I can think of BFSS is the holography if I approach a stack of D0 branes. So I can think of IKKT as holography when I approach a stack of D instantons. Right, and in the end, the matrix model is just the matrix model that lives on a stack of the instantons. So in that sense, it's a bit like ADS5 cross S5 and n equal 4 superior mills. You just always speak out the world volume theory of the stack of branes, no?
I see what you mean. That's true. In fact, That just saying that. Well, it's in the framework in the formalism of matrix model, it's hard to derive. I mean, the dictionary in an explicit way. Just you don't see the CFT in the usual way. So that's right. In that sense, I was saying that like the holographic setup is not obvious, but you're right. Of course, it should all be there. Yeah.
Okay, thank you.
Yes. The big issue is, does the partition function factorize? So is it true that the partition function of z to the power of n is really the single system partition function to the power of n? Well, plus small corrections. I mean, I expect that this can happen, but I mean, is this true at least at leading order or not? Just as we discussed, I mean, this is certainly relevant in the context of ADS CFT if you look at it the proper way, but also, I mean, in general, I mean, do we expect factorization for strings and D-branes or not? So the plan is compute z and z to the power of n specifically for n equal 2 and 4. I mean, this is z equal 4 is enough to see both wormholes and half-wormholes, so that's easier than working with the general n. I mean, it would be very complicated not to fix n, and it doesn't matter here whether it's quenched or annealed. One can detect non-factorization either way. Here, I will specifically find the saddle points both factorizing and non-factorizing, but another way to do it, like in Engelhardt and co-workers' paper. So you look at the quenched partition function, you look at the quenched free energy and the annealed free energy, and when these two do not, when these two differ, then actually that's really a sign of non-factorization. But yeah, I find it more transparent to just explicitly find wormhole and half-wormhole solutions in with the annealed partition function. And then the formal trick, very well known from the SYK literature, but actually much older than that, is just introduce the collective fields. And here I want to be short, unless, if anyone's interested, please ask for details, but I will gloss over the calculations perhaps without going into detail, because it's rather straightforward. So this bilinear A dagger A will appear in the partition function. So instead you introduce the collective field G, and then you write out the Dirac delta functional in terms of the Hubbard-Stratonovich auxiliary field, and then the rest is just algebra. You can find the solution and compute the effective action. Okay, so that's for a single replica. The real thing is what happens with 2 and with 4 replicas. So let's jump to 4 immediately. So we can call them, left, right, left prime, and right prime. So yeah, first you go to z squared, where we have the left and right copy, and then each of these copies is again doubled. Then we have two field combinations and 4 field combinations of bosons. So yeah, G small is 2 field combinations, and G capital is 4 field combinations. So yeah, 2 field combinations are left, right, and 4 field can be any. So yeah, any combination of these 4. That's for bosons, and then for the fermions, this bilinear will also appear. Actually, yeah, the fermionic part is really quite similar to what is known for SYK, what was done in the paper by Sads and others from last year. For bosons, it's a bit different. It's actually a bit more complicated, but yeah, at the end of the day, you can write the effective action in terms of the collective fields, and then you just solve the saddle point equations for the Hubbard-Stratonovich fields for bosons and for fermions. So yeah, you can regard these as wormhole couplings, like the left-right couplings. These are like wormholes. And then you also have half-wormhole couplings between left and left prime and right prime. So yeah, there are several solutions, but not all of them. Well, only one of them is preferred, right? So I will not give the full expressions. I mean, it can be found analytically perturbatively, like in expanding in 1 over n. Let me just say that, okay, there's trivial solution when everything just 0. I mean, when you put all fluctuations to 0, of course, that's trivially factorizing, but that doesn't make, that's not very interesting, and it's never preferred. Then there's a wormhole which doesn't factorize. There's half-wormhole which does factorize, and then there's wormhole plus half-wormhole, which also factorizes. So this half-wormhole just precisely cancels out the non-factorizing contribution of the wormhole. And it is this last solution which is thermodynamically preferred, so which minimizes the action. So the wormhole saddle is can diagrammatically present it like this. So left and right are coupled, then half wormhole where you have left and left prime, and right prime. So there's no wormhole. It's 2 replica level. Only when you have 4 replicas you have you have some couplings in between. And then wormholes plus half wormhole. Well, that means that you, so you connect both left, right, and left, left prime, right, right prime. And this solution turns out to be thermodynamically preferred. So here, I checked this numerically. So blue is the analytical result. Red is numerical for n equal about 100, I think. Sorry, I didn't write n, but it's about 100. Well, the larger n, the better the agreement should be. But of course, you also have the problem that the numeric starts hiccuping at very large n. So for n about 100, the numeric still works great. And as you can see, the analytical and numerical blue and red curves almost coincide. So that's okay. And then you can compare the 4 replica action, which is this colored curve, whichever of these. You can compare it to 4 single copies, black dash, and indeed you can see that the factorization is near perfect. Well, not perfect, as I said, because I expect that finite n effects will always spoil it to some extent. But quite obviously, I mean, at leading order, it's a good approximation. So generically, it may or may not factorize, but it seems that the factorizing solution is preferred, and it's actually easy to show that it does not depend on p. I mean, on the brane dimension. So I mean, for p equal 1, it's easier to do the calculations than for larger p. But when you just look at the effective action, I mean, you see that it would just it would go all the same with also with D3 branes, D5, and so forth. Okay, so this was for 2 parallel strings. Now for non-BPS or for interacting system, well, it gets more complex. And again, I propose not to go into full details. This is just for completeness. I mean, to convince you that that I did the calculation. I mean, I'm not, I'm not just telling stories, but I mean, it's all straightforward still, matrix algebra, but it just, the equations are longer. And it turns out that, that's again, the dominant contribution is factorizing. But then what is interesting here is that one and the same contribution, which comes essentially from the Hubbard-Stratonovich field, or from integrating over the original fluctuations, a mu dagger. It turns out that it's always one and the same term in the partition function, which is dominant. Previously, it wasn't the case. The factorization was non-trivial. So in the sense that, I can go back with 4 replicas. That with a single replica, it's again this Hubbard-Stratonovich contribution, which is dominant, whereas with the 4 replica system, with wormhole plus half wormhole solution, it's this part which is dominant. So I would call that non-trivial factorization. So it's not like with n replicas, you just at leading order have one in the same term times n, but it's like different terms conspire to cancel out the wormhole's contribution and to contribute to factorization. But that's only for the BPS solution. Here, it's what you could call trivial factorization. Just one in the same term is always dominant. So in all cases, the minimal action solution factorizes. In interacting systems, the factorization is trivial, whereas in a BPS protected system, it's non-trivial. I don't really understand yet what this means. So I find it interesting that these partition functions always factorize at leading order, at least. That may have to do with the fact that, as we discussed, secretly, I mean, this IKKT model knows about holography all the time. Because in principle, I could think of meaningful systems, say in statistical mechanics, where it's not necessarily true, but here it is. And now I go to the second part about chaos and OTOC in the matrix model. So if there are any questions about this first part. Okay, if not, then yeah, can we relate actually this factorization and non-factorization to chaos? And in general, yeah, what would this look like? What would this look like in the matrix model? Now, the terminology is a bit confusing here. So there are several ways that you could talk of quantum chaos in the matrix model. And actually, I have seen the quotation several parts and actually attributed to several people. I mean, most often to Boris Chirikov, but I have also seen it's attributed to a few other guys, interestingly. But it's kind of standard lore in quantum chaos literature. So anyone who uses the words quantum and chaos in the same sentence should be hung on a tree in the park behind the Niels Bohr Institute. This mainly in relation to, well, in relation to the fact that, I mean, Niels Bohr Institute in relation to the fact that, well, I mean, in, well, normally the Schrödinger equation is linear, so you certainly don't have chaos, quantum chaos in the very literal sense of the word. And also, well, in old quantum mechanics, people mainly looked at, right? People mainly looked at integrable systems, which can be quantized by quantizing the action, the Bohr way. Okay, nowadays we know that this is simply because, well, it's classical mechanics that was too primitive back then. I mean, now thanks to Gutzwiller and so forth, we know how to quantize in the same way also non-integrable systems. But at any rate, so what's chaos here? So first thing that comes to mind is, of course, to just look at to just look at the eigenvalues of these matrices, these fluctuations. I mean, that's very obvious. And look at the eigenvalue statistics. That's quantum chaos proper. But then the orthogonal way is to look instead at, well, at how the system, well, at the non-equilibrium chaos, if you wish, because, well, OTOC is, yeah, it's really orthogonal to, I mean, to level statistics. I mean, it's really about how system behaves when you knock it a bit out of equilibrium, and there you really have time dependence and Lyapunov exponent, and we'll see that these two behave rather differently. Yeah, I mean, they tell you different things in regards to factorization. So let's first look at level statistics. I mean, you just plot the energy level spacings. I mean, the spacings between adjacent levels. And then if you can fit it to the Poisson distribution, the black curves, then it's close to integrable. If you can fit it to Gaussian unitary ensemble, the red curve, then it's well, to a Gaussian ensemble in this case, because we have complex matrices with yeah, with time reversal invariance, then it's Gaussian unitary. So yeah, if you can fit it to the red curve, then it's yeah, then we say it's chaotic. So okay, forget about the trivial saddle. I mean, when everything's zero, then yeah, the wormhole saddle, you see, it's mostly regular level statistics. So yeah, it's non-factorizing, it's regular, and yeah, it's self-averaging in the sense that the typical, yeah, in the sense that the typical value of the partition function is kind of close to the average value. I deliberately did not want to talk about that now. I mean, it's discussed a little bit in the paper, but yeah, let's not go into that now, at least until the time for, I mean, at least not till the end, because I want to, yeah, I want to cover some more material. So the half-wormhole saddle, it's chaotic. It's very well fit by the Wigner-Dyson curve. And that's already factorizing, as you know. And then wormhole plus half-wormhole, it's still factorizing, and it's yeah, and it's still chaotic. So apparently, well, factorizing and chaotic go hand in hand, but we want to understand this better. So let's look at dynamics. So now it makes sense to go back to Lorentzian signature, obviously, and to ask the question, well, how to introduce dynamics? It's zero-dimensional. So in BFSS, it would be easy, but what's dynamics here? So now one has to differentiate between annealed and quenched regime. So the annealed regime is, well, what we were looking at so far, and and actually there's a trick in the literature on how you can, yeah, on how you can arrive at time. You basically look at correlation between the eigenvalues of the of the time matrix A naught and the spatial matrix and the spatial matrices. And in this case, I mean, this will be necessary later. So the whole action scales with n. So the fluctuations stay of order unity, roughly speaking. Then in the quenched limit, it's really a Eguchi-Kawai model. So to remind, Eguchi-Kawai is really discretization of Young-Mills, so of gauge theory on a lattice. So in that case, actually the action is formally the same as IKKT. I mean, it turns out that the derivatives drop out, and basically from the self-interaction from of the gauge fields, I mean from the non-commuting contribution to the field strength tensor F mu nu, you get these, well, A mu A nu commutator squared. So, and this turns out to be the only surviving contribution in the discretized case. So this is a Eguchi-Kawai model. And so it's the same action, but it corresponds to the quenched regime. In this case, in particular, the A naught, the leading component of the time matrix, so that has to be quenched because that acts as discretized time derivative. So you can regard it as matrix with frequencies, or well, frequency differences on the diagonal. And then when you commute with A naught, that's basically like time derivative. And in this case, it turns out you have to rescale it. So the action is rescaled, and therefore the fluctuations also. So I will mainly talk about this regime. I mean, this only if time permits. But this is also more interesting and more directly related to, I mean, to strings and branes that we were looking at so far. Now, this was proposed originally for cosmological applications, so this way of introducing dynamics. This is the first paper I'm aware of by Nishimura, Tsuchiya, Kim, and Ito. I think it's the first one. Maybe I missed some earlier publication. I'm not sure. So the recipe is the following: consider A naught as the time operator, and its eigenvalues as discrete time increments. So let's go to the eigenbasis of A naught. In this case, the A naught matrix is diagonal, and let's sort the eigenvalues in ascending order in this direction. Then time instants are kind of sums of these time increments, and the state of spatial coordinates, spatial matrices at some point this time is really this n by n block on the diagonal, which as you move along the diagonal. So this is motivated by the fact that even though, of course, you can for any finite n, you can diagonalize these matrices simultaneously. But as you see, I mean, when in the eigenbasis of A naught, this A1 is not that far from diagonal, right? So in log plot, it becomes much more obvious. So this is just the log plot. So then you can see, so A naught diagonal and its eigenvalues, time increments. And here you can really clearly see, I mean, the scaling that, I mean, far away from the main diagonal, there's really nothing. So you can really say that, so, okay, at time equals 0, this is really the state of the A1 coordinate. And then as you move along the diagonal, so since these off diagonal elements they decay so rapidly, you can say that this submatrix is really the state of A1 and of spatial matrices at a certain instant in time. And then defining the OTOC proceeds easily. So the usual definition can be applied just to coordinate matrices. So these are then really, I mean, like Lyapunov exponents for the coordinates, except that now it's not only the commutator of x and its conjugate momentum, which is non-zero and non-trivial, but in this case you also have actually the commutators between two different spatial coordinates still behaving non-trivially, of course, because it's quantum fluctuations, right? It's not, that's the whole point. I mean, it's not classical space-time anymore. So when you write out this commutator, so remember the instant in time, it's really, so the time instant is really, so you sum a number of temporal eigenvalues starting from some I capital. So this I capital, that's really your time instant. I mean, you instead of time, you can look at the you can look at I as the cardinal number of this increment. So in that case, xi is just x at time ti, and y naught is y at time 0. So you can see that this is really just like the textbook OTOC. And when you write this out, as we know, so actually, well, this is the textbook, well, commutator squared, well, module squared of the commutator. And then when you write it out, it turns out it's a difference of TOC and OTOC times 2. And then TOC is, well, the time order contribution, xi times y0, versus OTOC is time disordered, I0, I0. And then the crucial trick to obtain at least some analytical insight, I mean, it's crucial to also do the Monte Carlo numerics, but yeah, to some extent you can understand it also by separating into the diagonal elements and off-diagonal elements, because again, as I said, we expect that it's still true the diagonal elements are much larger and yeah, have kind of more regular dynamics. So schematically, when you write it out, this is what you get. So you always have this slow contribution, but then because you subtract OTOC from TOC, then actually, yeah, this will cancel out. And then the leading contributions are these. So yeah, these products plus sub-leading terms. So yeah, the tilde matrices here are just off diagonal components. So Q and P are the diagonal ones, and yeah, tilde is and X small tilde and Y small tilde are the fluctuations. Yeah. So from both numerics and from well, large N expansion, it turns out that these diagonal components, modulo squared, these grow exponentially with time. And actually, yeah, this time growth is what normally interpreted as cosmology in IKKT model. So this was the big finding about 10 years ago, that only 3 spatial dimensions actually grow exponentially large, whereas the other ones stay small. But that's a different setup. I mean, it's essential to have fermions and to integrate them out. And then when you get this Pfaffy, and then it turns out that this SO9 symmetry is broken. Here I disregard the fermions completely. So yeah, everything stays isotropic. So this has nothing to do with cosmology. It's more abstract. It's more like proof of concept, but it's still true that you have exponential growth of these diagonal terms. So altogether, TOC minus OTOC, so the whole correlation function. So it has these exponentially growing contribution plus sub-leading terms. Now it's tempting to claim the exponent R is the Lyapunov exponent, but that's completely wrong when you think of it, because this is the whole thing TOC minus OTOC. Whereas we only expect OTOC to have exponential growth, and that's why the whole commutator goes down, because it TOC minus OTOC and OTOC goes up. Whereas TOC normally in field theories, well, it should factor out and saturate to a constant at long times. At least that's the standard law, right? I mean, that's, well, it should all factorize out, and therefore TOC just becomes the product of x squared times y squared, and therefore TOC doesn't do anything interesting, and it's just OTOC growth which contains chaos. But here it's not like that. So here TOC is non-stationary, so there's no equilibrium solution. I mean, it's some non-stationary geometry. As I said, in this context, it cannot be interpreted cosmologically, but yeah, well, as I said, there are several loose ends here. So one thing that I want to understand is really what this is. So yeah, it's some non-stationary geometry for sure. And at any rate, so this exponential growth, it has nothing to do with chaos. You can also see that from numerics. So blue or C plus is the is TOC, OTOC is red or C minus, and they're double difference, so the whole commutator is in violet. So you can see that you can see that TOC and their difference, I mean, they grow exponentially large, whereas when you zoom in at OTOC, well, it has some growth, but it's much weaker. It's sub-exponential. You can also do the log lim plot of this left side figure, and then you see that again TOC is nice, has a nice exponential growth, whereas OTOC, well, unfortunately it's a bit noisy. I mean, you need larger matrices. This is n equal 144, I mean, but one should go up. So yeah, it's a bit noisy because it's much smaller. Here it even looks like, well, it could be exponential, but it turns out that you actually get a much better fit on log-log plot. So it's actually some power law. So here I have also plotted the TOC, but with the exponential growth explicitly. So yeah, explicitly canceled out. So when you cancel out this, you see that that it doesn't do anything else except for having this overall trend. Whereas OTOC actually has some growth, but just as you would expect for a weak chaos, it's not it's not exponential, but a power law. It would be too much, I mean, to claim that this exponent 3 has some physical significance. I mean, maybe it does, but I don't understand it yet. So yeah, I don't know yet what it means. As I said, first the TOC should be understood, and then we should understand in more detail the weak chaos shown by OTOC. So why is it so that that OTOC only shows weak sub-exponential growth, whereas we have seen beautiful, if you remember, we have seen beautiful Wigner-Dyson level statistics. So this one more proof that these two don't necessarily go hand in hand. I mean, they're different things. So in this case, it really matters that we're looking at the anneal system and not quenched, because OTOC is an expectation value. So previously, when we were looking at partition functions, I mean, once you average over the slow variables, you don't integrate over the fast variables, but on the contrary, we were just looking at saddle points, like solving the equations of motion. But here, because we're looking at the correlation function, we also eventually sum overall overall configurations of this fast variable too. I mean, as like always when you're computing expectation values. So it doesn't make sense to ask, when you're looking at OTOC, it doesn't make sense to ask which of those saddle points contributes. They all contribute, right? I mean, saddle point solutions is just, right, you find a certain a mu, whereas here you just integrate over a mu to find the to find expectation value. So we really include the contributions of all these saddle points, including the completely non-chaotic ones. So in that sense, you can see, I mean, that you don't at any rate, you don't expect to see strong chaos. At best, you can see a superpositions of strong and weak chaos. So what also remains to be done is to try to somehow, although that, maybe to introduce some additional potential, but as soon as you do that, you're not in string theory anymore. So basically, to try to somehow focus at this, say, half-wormhole saddle point, and to see what auto corresponds to that one. That's that's a point to ponder for sure. Now the quench case, Eguchi-Kawai, that actually, I won't talk about that in detail. I can just say that in this case, actually, when you quench a knot and interpret it as time derivative, it actually becomes very similar to S5K, because again, this commutator square, that gives you like 4 matrix interaction, which is the same as you have in S5K, though it's bosons here, not fermions. But it becomes very similar, and actually you can just go through the original argument by Kitaev and others. And you find, of course, in that case, you find exponential auto growth, which is universal and something like maximal chaos. But that had to happen, as I said, because first you expect it in a first you expect it in a young Mills, and second, well, as soon as your SYK like, then I mean that's that's a very well known system where we know very well how to do calculations. Actually, that's why it became so notorious, because it's amenable to calculations, and it still makes some physical sense. So is there a morale to the story? Factorization is generically obtained in also independently of also when you don't require it specifically. I mean, for the from the CFT viewpoint, it's just there. Though you can also find non-factorizing solutions, and there's a correlation between chaoticity and half-wormholes, or in other words, factorization. Now it's also possible to look at OTOC and time-dependent dynamics in general. I mean, I think it's a potentially fruitful field, because it's a way to do non-perturbative string dynamics, not only for cosmological applications, but also many other things. So in the annealed case, you sum over all the saddles, and the outcome is weak chaos. But then the crucial thing to understand is there is there a geometric or a gravity interpretation in the classical limit of the whole thing? So thanks for attention. If there are any questions, please.
Thank you very much, Mihailo, for this very nice overview on new stuff. Questions? It looks like Kevin has unmuted himself. Can Kevin?
Yeah, sorry, I was trying. I don't know how. There we go. Sorry, I was trying to figure out how to raise my hand, but
forget about it. It's okay.
Yeah, I just want to make clear that I understand. At some point in your talk, you mentioned that the thermodynamically favored solution was this mixture of wormhole and half-wormhole, and that it had factorization. And then I think you said that it might, that perhaps that is because, despite of your first statement here, that factorization is obtained generically independently of ADS-CFT, but perhaps that the thermodynamically favored solution does have factorization. You think that has to do with the fact that Type IIB secretly has holography, or no?
You mean that, okay, that the really, okay, that the true solution has to be like this because it has, because IKKT has holography.
That's right.
Well, frankly, I don't know. I mean, it's tempting to say so. It makes sense, but just I cannot provide any specific derivation. I mean, what one would like to do is to, I mean, at least to compute the partition function and say, look, I mean, this partition function equals the Young-Mills partition function when you identify, I don't know, n with this thing, and I don't know, this, when you identify the parameters, but I don't know how to do that. I mean, this n of IKKT is not the same, or at least not at face value the same as n in SUN Young-Mills. Because I mean, this n is about discretization. So what you say makes perfect sense to me, but frankly, I cannot do a calculation which proves it explicitly. As far as I'm aware, I mean, nobody has done this explicitly in the IKKT model. If well, please correct me if I'm wrong, but as far as I know, I mean, we all know it's true, but I don't think that we have a matrix derivation of ADS-CFT yet.
Good. Thank you.
Any other questions? I had a simple question because I didn't see it. I didn't follow. There is the do the diagonal matrix that you had drawn, this 144 by, yeah. I'm just trying to understand this. Does this have anything to do with eigenstate thermalization?
Oh,
because what I'm thinking is that the off-diagonal, basically your statement was that of what people state about eigenstate the thermalization hypothesis, that your system has is described by a density matrix which has off-diagonal elements which are atypical and therefore very quickly very close to zero, and the diagonal elements are the typical, describing typical states which are behaving quasi-equilibrated, if I can use fuzzy language, because it's not very pregnant, well, it's not very mathematical, I would say. But yeah, so that's what this reminded me of, and I just wondered if what this could have to do with that. Maybe it's just not really.
Well, that's a great idea, yeah, to think about that. So yeah, well, what's a bit different here is that you have kind of I mean, okay, I should have included also a 1D plot. I mean, when you look at it, it has kind of two scales. I mean, it's not like just exponentially going down away from the, away from the main diagonal. I mean, it is going down as soon as, I mean, as you can see, as soon as you move away from the diagonal, it goes down. But then you have an additional scale when it really abruptly drops to near zero. You know, it's like here going down, but then at some point it really, like, you know, so in that sense it's different from eigenstate thermalization, where, as far as I remember, normally you just say that, okay, all of diagonal elements are e2 minus n, and that's all. But okay, I mean, this is okay. Yeah, you would expect that super young Mills, I mean, satisfied eigenstate thermalization. So in this quenched regime, it's definitely true. But when you don't quench a knot, which indeed is quite crucial here, I mean, you just allow it to be whatever it is and diagonalize it. Yeah, well,
just
yeah. So I don't know exactly, but I certainly agree that the idea to think about it, as I said, purely phenomenologically, one thing that differs is that you have these two scales. So like fall off, and then a sudden much sharper fall off.
Yeah, that's interesting. So, okay, are there any other questions? Okay, if that's not the case, then we can first thank you again, Mihailo.
You're welcome.
And we'll finish the recording.